Okay, chapter 4.5, we have a two-part video today, and this first one's going to be kind of rushed because I'm trying to do it in 2 parts instead of 3. So first of all, I hope everyone had a good, relaxing spring break. At least you didn't have to do any work, right, for school. But let's just start here with example 1. This is going to be a combination of everything that we've learned in this entire chapter up to this point. This is an exponential equation, and in section 4.2, we discussed how you could actually try to get the bases to be the same, and then just set the exponents equal to each other and solve. The problem with this is that, no matter what I do to the 7 and the 12, I don't think I can get the exponents, to be the same, or to get the bases to be the same in my head. That's just it's gonna require more thinking ability than what I really want to do. So in the situation where you have an x on one side and you have uncommon bases, your bases are not the same, then the easiest thing to do is to rewrite this to, for example, if it's in exponential form, let's rewrite this as a logarithm, okay? So this is the same thing as saying log base 7 of 12 is equal to the exponent, so it's equal to x. And once you get it like this, then hopefully you guys can see the log base 7 of 12 is just a simple change of base formula, or the evaluating of the logs that we did in 4.4. So if we do change of base, that's log 12 divided by log of 7 in the calculator. And, for those of you who have the button for the graphing calculator, then that should make this easy, but that should give us approximately 1.277, okay? Now, I only rounded this one to 3 decimals, but on your test, I'll probably, indicate exactly how far to round it. It's probably going to be 3 or 4, just depending on the problem, okay? Let's skip example 2 for a minute just because it's a little bit harder, and let's look at example 3. Now, the whole first page of notes is all about exponential equations, and then there's 3 logarithm equations on the back. So that's why this is kind of a 2-part section, because you do have to do 2 different things. Now, this exponential equation, we do have common bases. They do have a base of e. Actually, all 3 of them do. However, we don't have, and we have x on one side, but the x is not in one spot. You have 2 bases that have an x. So just like, for example, if I had 3 squared times 3 to the 4, just like if I had this and I said, okay, I want you to condense it for me, rules of exponents say that when you are multiplying, that you actually add your bases together. So that's exactly what we're going to do here in example 3. We're going to add our bases, or not add our bases, but add our exponents together. So that's going to give us something along these lines. If I condense it a little further, it should be negative 2x plus 1 is equal to 3e. Okay? So easy peasy there, right? And just to make this a little bit neater, I kind of want it to look more like the first problem where we had one base on one side. In the first problem, our base was 7. Our answer was 12. Well, over here, I have a base of e, but it happens to be on 2 sides. This is actually e to the first over here, if you think about it like that. So if I want to get rid of the e on this side, I could just simply divide both sides by e to the first. Okay? Now, that's just going to cancel that out and leave us with a 3. And over here on the left side, when you are, when you're dividing exponents with common bases, then you subtract the exponents. So what we're really doing here is we're saying, okay, negative 2x plus 1 minus 1. And that's going to end up leaving us with e to the negative 2x, because the 1's will just end up canceling each other out. Okay, so now we have this problem, and it's not done yet. I'm just boxing it off to kind of keep it organized to show you where we're at. And although it has an e, it looks very much so like our first problem. So we just now need to rewrite this as a logarithm. Okay, now if I rewrote this as a logarithm, we would have log base e of 3 is equal to negative 2x. And guys, hopefully right now, something's dinging in your head going, oh, well, wait a minute. Log base e is actually the same thing as the natural log of 3 is equal to negative 2x, okay? Now, you could go ahead and put the natural log of 3 in the calculator and get that decimal, but I think it would just clean it up and be a little bit more accurate to go ahead and divide both sides by negative 2, and then just put this whole thing in the calculator and see what you get. So if you do that, if you just put that whole thing in the calculator and hit enter, then you're going to get, I keep putting equal, it's approximately negative 0.5493. And I just went ahead and rounded that to 4 decimal places instead of 3. Okay? Let me see how much time I got left. I'm going to try and squeeze this. Oh yeah, I got plenty of time. I'm going to go ahead and do this middle problem now. And I'm going to go ahead and tell you that it is a long problem. You might need some extra paper. And fun fact of the day, I've recorded this video about 7 times and couldn't figure out why I wasn't getting the right answer. And then it dawned on me that I had the notes typed wrong. I had put 2x plus 1 in my original notes when it was supposed to be minus 1. So I've had to redo this video probably 6 times because of that. But it's okay. I got it all figured out now. Just to clarify what makes this example harder and how it's different from the first two, first of all, it has an x on both sides. You have an x and the exponent on the left and the right. And second of all, it doesn't have a common base. In example 3, our common base was e. In example 1, we had one base, which was just 7. So we're dealing with kind of a double whammy of problems here, okay? And if you see this kind of problem come up in your homework, and I haven't decided if I'm putting it on the test, but if I do, then the first thing that you need to do is actually to multiply log base 10 to both sides. And log base 10 is just, log. It's the common log. So you don't have to do anything crazy. You just put this. You're probably wondering, okay, well, what's the point of this? Why would I multiply, the common log on both sides? Well, if we didn't have a common base to begin with, by multiplying log base 10 to both sides, it's now going to give us a common base of 10. So we're just trying to make this more consistent and, so that we can actually continue solving it from here. But now that you've multiplied log base 10 on both sides, and that's legal, by the way, because it's an equation. So if you do something to one side, no matter how crazy it is, as long as you do it the same thing to the other side, then it's okay. Essentially, we still have the same problem, just written differently. So, but once you do this, now all of those the properties of the logarithms and all of those rules that we've talked about previously apply to this problem. So the power property of logarithms says that, hey, if I have a log with a power, that can actually come out in the front and be multiplied in the front. So now what we have is we have 2x minus 1 times log of 3 is equal to x plus 2 times log of 0.4. So the more we keep going, kind of the cleaner that it looks. And I want to take a minute and just have you guys reflect for a second. If this number right here and this number right here, if that were just a 3 and a 0.4, and that log was not in front, then I think it would be easy to see that all we'd have to do is to distribute that inside the parentheses. Our goal here, by the way, is to get x on one side by itself. That's any goal of an equation, is to just get x on one side by itself. So if you didn't have that log there, it would be pretty clear to know that you had to distribute. It's a little more confusing when the log is there, but that's actually what we're about to do. We're going to distribute log 3 to the 2x into the negative 1. So now we're going to have 2x log, not log 2, but log 3, minus log 3. And then we're going to do the same thing on the other side. We're going to distribute log 0.4 to both sides. So you're going to have x log 0.4 plus 2 log 0.4. Okay, so getting a little bit closer, keep our goal in mind. Our goal is to get x on one side. So just like any other equation, I want to move all of my x's onto one side. So I'm actually going to move my x log 0.4 over here. Okay, so now I'm going to have 2x log 3 minus x log 0.4. And then, once I've got all of my x's on one side, and I'll do this in a different color, I actually want to move my, I hate to call them real numbers, but that's what they are. I want to move all my real numbers to the other side. So that's going to leave me with 2 log 0.4 plus log 3. Okay? Now, as messy as this looks, because it almost looks messier than when we started, we're so close to the answer, okay? We really are. As much as I would love to be able to combine these two terms right here with the x's, as much as I'd love to combine those, it's not possible. But what is possible is, since both terms do have an x in them, we can factor an x out. Okay, so I'm going to come over here and I'm going to finish my problem on the right side. If I factor an x out of all of those two terms on the left there, that's going to leave me with x, and then remember, you have to come back and divide and put this in parentheses, but it's going to leave me with 2 log 3 minus log 0.4. That's a 4, not a 9. Okay, and that's going to equal all of this crazy stuff that we still have going on over here on the right. Okay, we're almost there. Remember, our goal is to get the x by itself. So, if the x is being multiplied by something, we can divide to get rid of it. And so that's what we're going to do. Amazing how all this stuff relates, huh? Never would have thought to do this with logarithms, but here we are. Okay, now the good news is all that cancels out, and we now know what x equals. It's equal to all this, but that doesn't help us. We have to turn it into a number that's, we can actually understand. So if you're really calculator savvy, you can probably just type all that in and get a good answer, but I'm going to condense it as far as I can go to try to clean it up a little bit. Of course, I know this is going to become the exponents for those two numbers. So this will be log 0.4 squared plus log of 3 over log 3 squared minus log of 0.4. And just to clean it up a slight bit more, hopefully you guys remember what to do with these. You remember what to do with those two numbers if your logarithm is being added, okay? So in this situation, if we're adding, we multiply those two numbers together. So you say 0.4 squared times 3, which, by the way, gives us a log of 0.48, divided by, and then down here, if they're being subtracted, we divide these two numbers. So you're actually going to say 3 squared divided by 0.4, which is going to give us, and this, I didn't actually turn this into a decimal. I wanted it to stay as accurate as possible, so I just left it as 9 divided by 0.4. But after it's all said and done, you're going to get a value of x is equal to approximately negative 0.236.